So in this video, I'm going to go over the right-hand rule. Make sure you understand the general idea of the right-hand rule for vector cross products. It's a general rule. Once you understand it, right, you can apply it to anything from graphics pipelines, which uses a right-hand coordinate system, or a right-handed spiral, or a right-threaded screw, and so on. So the basic idea that you have to know is that we know that a vector cross product, so this is a mathematical definition. So A cross B, and if you remember, there's two definitions we could write. One is one with the determinants, right? The determinant of ijk and A. So one way is we could write the determinant in terms of ijk and write the components of our vectors bx, by, and bc. So algebraically we can solve this, assuming, of course, that the vectors A is axi plus ayj plus azk, and b vector is equal to bxi plus byj please pzk. Okay, so this is the first definition. We also have an alternative definition, is that it is graphically we have two vectors A and B, and there's an angle between them called theta. Let's call this theta, yeah. And so the second definition of vector cross product is equal to the magnitude of A times the magnitude of B times the angle between them times a unit normal vector. So this is our unit normal vector. So the unit normal vector is perpendicular to both A and B. But if you look at these two vectors, assume that A and B are in the plane of the board. So we have two choices. The vector is coming out of the board. The normal vector could be coming out of the board or going into the board, because this normal vector is mutually perpendicular to both A and B. Okay, so we know that, so we can actually prove it very easily, actually. But this normal vector is perpendicular to both A and B. Okay, so going into the board or out of the board. So we don't know. So our mathematical system is based on something called the right-hand coordinate basis. And the right-hand coordinate basis assumes that we have I cross j is equal to k, but a direction. And this is the direction, the right-hand rule that I'd like to make sure you understand. So the basic idea we're going to understand is that imagine that A is this way. A is a vector that's pointing in this direction, and B is a vector pointing in this direction. So A is the first vector, and B is the second vector. So when A turns into B, we kind of rotate A into B like this. So it's the smallest angle between A and B. So here's A, here is B, and the smallest angle between A and B is this, from here to here, and I'm turning from here to here. So take out your right hand, and see which way you have to turn your fingers to turn from A to B. So your fingers, not your thumb, excluding your thumb. So assume your first four fingers, which is your index, middle, ring, and pinky fingers, right? So they're turning. So they form a direction. So they turn this way or this way. Okay, so if I have an axis like this, if I want to turn this way, I take this curve and turn this way. So my fingers form a kind of an arrow. So my fingers, I'm a terrible drawer, but I'll do it this way. So here's my fingers, and here's my rest of my hand. Horrible. But here's my fingers. They're turning in a certain direction. Of course, I could point in the other direction. My fingers could be pointing in the other direction. Here's my hand. And can I see this on the board? Kind of. So it's this way or this way. And they're actually causing a rotation. Your fingers form a kind of a rotation. They're directing a direct rotation. So the idea is that if I take A, here's your A, and here's your B, I'm turning A into B, the first vector into the second vector. A into B. So I'm turning this way, this way. And notice the direction of my thumb is going into the board, and that's the direction of the normal vector. So A normal vector that's going into the board is going to be denoted by an X. So remember, a vector that's drawn into the board is drawn with an X. It's supposed to be the back end of an arrow, and you're seeing the feathers of the arrow, which is at the end. And if something is coming out of the board, so into board, and going out of the board, right? You're seeing the tip of the arrow. So you remember, an arrow basically is the front end, which is a little point, and then it's got some feathers at the end of the arrow. And so when it's going into the board, the arrow is facing away from you and going into the board. So in this case, A cross B, the normal vector that's perpendicular to the right-hand rule, right, is, so here's our A, here's our B, and we're turning A into B, so I'm turning this way. With my right hand, take out your right hand and turn in that direction. So if I turn in that direction, you'll see my thumb is pointing into the board. So I'll put it sideways so you can see it's going into the board. And so our normal vector n hat is actually written into the board. So the vector cross product is a vector that's perpendicular to both A and B, and it's going into the board in this case. So let me do some examples of this, right, so that we can actually make sure you understand the rule for the vector cross product. Let me erase this. And then get the orientation. So there are many rules for the right hand. There are many right-hand rules, and so if we did electric wires and finding the magnetic field, looking at the velocity of a force, the magnetic force of a particle, traveling velocity v and a magnetic field b, we can use right-hand rules. There's many few of them. We can use this rule where basically one is of one vector and your things point another, and your forehand, right, represents another. Or some people actually use this rule. And actually, I always believe that these rules, right, are kind of like, they miss the point. They only apply to one little aspect. Once you understand the mathematical definition of the right-hand rule in terms of this curving rotation, you can apply it to many different things. So the basic idea that I want to try is, let's do some examples to make sure you understand the idea. Imagine that A is a vector A, and imagine that B is coming out of the board. So here's B vector. It's coming out of the board. Notice it's an arrow is coming out of the board. And I want to calculate the direction of A cross B. Notice I'm not looking for the magnitude. The magnitude is absolute A times absolute B times sine of the angle between them. Sine of the angle between them is 90 degrees because it's coming out of the board. A cross B, 90 degrees. Sine of 90 is 1. So we're not worried about that. We're worried about the orientation. What direction is the direction of A cross B? So here's your B vector, here's A, and I'm trying to calculate A to B. So basic idea, I'm going to draw A straight up. So here's my forearm. And B is coming out of the board, coming straight at you. And for me to get A cross B, A is the first vector, I have to turn A into B, like this. A into B, like this. So what I'm doing is I'm turning a rotation this way. So if you think about it, my rotation, right, is, so I have to take my right hand and I have to rotate this way. And if I rotate this way, I turn my A into B. And if I do this, my thumb is pointing in this direction. And if I know it's that direction, then the cross product is a vector. And maybe I'll redo this B so that it doesn't get in the way. I should have put it at the bottom. So here's our B vector coming out of the board. So again, here's our A, here's our B vector, okay? And A is turning into B, okay? Because A is turning into B, I'm taking my right hand and turning this way. A turning into B. And my thumb points in the direction this way, and so therefore my A cross B is a vector that is pointing in this direction. Remember, it's mutually perpendicular to both A and B, so I can't draw B perpendicular, but I can definitely write this and say A and A cross B are perpendicular. But remember, it's B vector and A cross B are also perpendicular. This is the orientation. Okay, so Hopefully you understood that idea. So let's try something more abstract. So let's try that if A vector is this way, and let's make B vector going into the board. So it's going in a diagonal. So this is B vector, and I'll put it at the bottom so I can see it better. So B vector is going into the board. So let's seem to be doing a lot of hand waving here. So here's our A. Here's our A vector. So you can't see me, but hopefully you can see it. It's going this way. B vector is going into the board. And I have to turn A into B, like this. A into B. And if I do, then the turning I have to do is take my right hand, so A turning into B, like this, is basically take my right hand, and I have to turn this way. I have to turn the A, which is this way, into B, so I have to turn this way. So again, let's do it over here. You're turning A into B. You're turning the A into B. Turning A into B like this. And that rotation is like this. And so what we get is that our thumb points in the direction. I'm using the right hand. Our thumb points in the direction of A cross B. Okay? So hopefully you got the general idea for A cross product. And let's do an example of this in a little more complicated sense. I think my marker is dying here. Let me get another one, see if this works. It's this thing better. So if I have a charged particle, oh, this is so much better. So we have the magnetic force acting on, classically, this is the magnetic force acting on a particle Q with charge Q traveling with the velocity V cross B. I'm going to assume that Q is positive just in the beginning. So it's positive, if positive. Okay? And if Q is positive, and the question is, let's imagine the velocity vector is coming out of the board. Here's the velocity vector. So the particle is traveling, a positive particle is traveling this way. Let's assume that the magnetic field is acting diagonally. So this is the magnetic field. So I know that I want to find the direction of the force acting on this particle. So the velocity, so we always remember that the magnetic force is QV cross B, QV cross B. So the velocity vector is this way. And let me do it this way. Here's the velocity vector V. Here's the magnetic field going down. Let's see if I do this. Going down like this. Okay, so the velocity is coming this way. And I have to turn the V, the velocity vector, into a B. Because remember, V is the first vector and B is the next. So I have to turn the V into B. So here's our magnetic field. Here is our velocity vector going down. This way. And I'm turning V into B like this. I'm turning V into B. And once I do, right, you'll notice that the process of turning, right, is this way. I have to take my right hand, I'm rotating the velocity vector from this way, so the velocity vector is coming this way. I'm turning it into B. I'm turning the smallest angle between V and B. Turning in this way. And if you notice, the direction of my thumb is pointing diagonally down, so it's going down this way. So the product of V cross B is going down diagonally. And so if I multiply it by a positive charge, I'm going to be scaling this vector more, and so the force, right, is actually perpendicular to the velocity vector which is coming out of the board. So the particle feels a force coming down this way. So if you kind of remember, right, remember particles in a uniform magnetic field, right, constant velocity, without dissipation, they'll actually form a circle. And the circle would be centered somewhere over on this line, and it would be circling like this, a positive particle. So it'll be circling like this. Okay, so it will form a centrifugal, actually it's just a circular motion. Okay, so hopefully you got the general idea of V cross B, and once you understand this idea, right, it's quite applicable to many other concepts. So the idea is that once you understand this rule saying that I'm rotating something from one vector to this using my fingers, okay, is this way or this way, right? That tells you an orientation of your thumb. And so the right hand rule can be used to calculate, for example, we can assume the same rule to find out the flow of conventional current. And actually I should do another example, but yeah, actually let me do another example just to make sure you understand the idea of F is equal to QV cross B, because that's what I wanted to make sure you understood when we did cross products. So imagine that somebody gives you an equation F. So the force of a magnetic field is given by V cross B. So it's not B cross V, it's V cross B. The force, magnetic force of a charged particle traveling with velocity V in a uniform magnetic field is given by QV cross B. And remember, we also mentioned in class, right, that that's equal to Q, and velocity is some kind of an L vector over some time cross B. So if the velocity is uniform, magnetic field is uniform, and charge is constant, it doesn't change magically from, so we're assuming a particle. Q over T is the amount of charge that travels a distance of L vector, a displacement L vector in a time T. And so this Q per T, right, can be thought of as a charge moving at displacement L in a certain time T, and this is actually defined as current. So we can actually think of a current, right, as equal to L cross B. So remember, so basically we still have a cross product, and so if somebody's asking you, okay, you have a current of wire, and here's your wire. Let's assume it's that, here's your wire. And so this is your displacement. Assume that this wire is attached to a battery, which I'm going to put a positive side here and attach it to this wire. So I'm going to look at this segment L. Okay, and it's in a magnetic field, and I'm going to assume the magnetic field is going this way, B. And the question is, what direction is this wire feeling? So I assume that the magnetic field is uniform along the wire. But so the direction of L vector is this way. For a piece of wire, it's carrying a current I. And remember, conventional current says that we attach the battery to the positive side, the longer terminal, and the shorter side is minus. And so we attach I into B. So the current is traveling along this wire, and what's the direction of the force on that wire? So we'll say here's L. Actually, maybe I'll do it this way. Here's L. And here is B. Okay, so here's L and B, and I have to turn L into B because it's the first vector, L cross B. The current I is positive. It's assumed positive. Conventional current is always positive. So we know that the charge carriers in wires, right, are actually negative electrons, but we always assume by convention that we always take the positive particles traveling in the opposite direction. So I is positive, L cross B. So we want to know the direction that this wire segment from here to here is actually feeling, the force that it's feeling. So here's L, here is B, and I'm turning L into B. L is the first vector, L, I'm turning into B. And so this turning motion, right, requires me to take my right hand and turn this way. So I'm turning into here. Hopefully you can see this, understand it, because it's difficult to write up. So if you look at my course notes, I didn't actually do this because the explanation is kind of difficult to explain, so I kind of skipped the main concept. And I'd rather just explain it to people in the lecture. So here is our length vector, here's our magnetic field, and here's our rotation from V to B. And my thumb points out of the board, coming this way towards you. And so our magnetic field force is going to be perpendicular to this, or specifically L cross B is perpendicular. So this wire feels a force being pulled out of the board this way, being pulled out of the board coming towards you. Okay, so basic idea, you should understand the right-hand rule for cross products and build up everything else. So it's kind of important that that rule, right, is applicable to cross products. We use mathematics to describe physics, and the reason we write this equation because of the cross product. Okay, so there's no equation that says that B cross B, no such equation. The equation for magnetic force, right, of a positive charged particle traveling with velocity v is V cross B, not B cross V. So be careful in this, okay? So where else can you use this right-hand rule? Actually, many things. So you want to apply the same rule, right? The basic same idea. Please try not to do this like right-hand rule, like with fingers or going like you'll never remember it. This general right-hand rule, right, once you understand cross product, you can apply it for many different things to explain. But the idea is that procedure of rotating. So for example, here's the current wire, and I'm assuming that conventional current, so it's positive carriers, which are basically electrons traveling in the opposite direction. So here's our positive carriers, which are really assuming that a conventional current is positive carriers, not negative electrons traveling the opposite direction. So here's a wire, and I want to know the direction of the magnetic field. So the direction of the magnetic field, we grab the wire, my right hand, and my thumb points in the direction of the current, and my fingers point in the rotation of the magnetic field. So basically, grab it with my right hand, not your left hand, but your right hand, and you'll see that the magnetic field is going around this way. So it's coming towards you. Fingers are pointing. So the magnetic field is coming towards you at this point. So the dots are arrows coming towards you. So it's coming this towards you, and then it's going down around the wire and then going into the board on this side. So here is. So the basic idea is that you grab the wire like this with your thumb pointing in the direction of the current. So it's one basic rule. Once you understand this, so the magnetic field is wrapping around this way. So once you understand this, right, we can also try the right-hand rule to explain the same right-hand rule with the fingers turning, right, can explain a right-handed spiral. What is a right-handed spiral? So imagine you have a stairwell. You have a stairwell in space. You have to visualize this. And every time I turn in the stairwell, I'm traveling a stairwell like this. I'm turning this way. I go up. My thumb points in the direction of going up. So take a spiral. So if I'm traveling like this, going around like this, you can't see the whole body, but going around like this, with my fingers pointing in the direction of me walking around that spiral. So if I do this spiral, I can't show it to you. I'm not very good at drawing, so I'll try. Here is the spiral coming in, and it's going behind, and then it's coming forward. So I'll put the solid as front, and the back, the dots are going into the back, and solid is coming forward. And oops, mistake. Dots for the back of that spiral, going forward, the front of the spiral like this. And this is, notice that if I turn this way, I'm going up my fingers. You'll actually notice that this is called a right-handed spiral. So the solid lines, oops, this is not solid, this should be a dots. The solid lines are in front of you, towards you, and the dotted lines are behind the board. Okay, so not very good, but so this is a right-handed spiral. So the direction of the rotation moves you forward. So what's a right-handed screw? If I have a right-handed screw, it means that if you see a screw, let's imagine that we have a right-handed screw, and this right-handed screw has it's got a Phillips slot, so you can use a Phillips head to turn this, right? So your choice, if it's a right-handed screw, which most screws are right-handed, so the question is, if I turn this way, notice my finger is pointing into the board, if I turn this way, the screw is going to go into the wall, because I'm turning this way and my finger points in the direction of motion. If I take a screw and I turn this way in the opposite direction, it comes out. Right-handed screws are basically done so that when you turn in one direction, they go into the board. If you turn in the opposite direction, they come out of the board. Okay, so that's a right-handed screw. So DNA, for example, is mostly right-handed spirals. It's a right-handed, DNA is mostly right-handed, but there are some portions of DNA which is DNA and B is right-handed, if I remember, and DNA Z is left-handed. So I'm sure you can find a Google video on that. But try to use this right-hand rule for everything. You don't want to memorize many different ideas, and at one point you're not thinking about simplicity, you're thinking about complexity by memorizing. So again, don't learn a language by reading a dictionary. Learn how to use the basic elements of the language by communicating. So don't memorize everything. So that never works. You should memorize a few things, few ideas, and try to see if you can reinforce those ideas. So here's the one idea that I really want you to learn: the right-hand rule by turning and twisting. So what else? I think that's everything, right? Right-hand spiral, right-hand screw, and yeah, so what's a left-handed spiral? A left-handed spiral or a left-handed screw. Left-handed screws are referred to as security screws. But so take a left-handed spiral. So I'll start at the bottom, so something in front, so it goes like this. It's coming in. So this is the front of the spiral, and then it's in the back, and then coming in. I'm very bad at drawing. The back is the dots. Oh, I messed that up completely. Messed that up. Okay, dot, 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 dot. So hopefully you got to saw this. So take out your left hand, the left-handed spiral. In the left-handed spiral, you're turning this way as you go up the spiral. You're turning this way. Okay? So it basically means that as I turn this way, as if I was standing here in a spiral staircase, as I go in the back, I'll be going up in this direction. And try not to say clockwise or anti-clockwise, because if you take the spiral and turn it upside down, you'll still have a left-handed spiral. A left-handed spiral doesn't change just because you turned it up in the 180 degrees. You should try to prove it to yourself. It's one of those subway car things, okay? So if you're in the middle of the subway and you have nothing else to think about, right? Take out a piece of paper and draw it out, do some calculations, okay? So basically the main idea in physics, okay, always spend a little time thinking, okay? It's not about you doing symbolic movement of symbols around. That's just math. Ideas in physics come out naturally, right, from ideas and thinking. So it's you thinking about these ideas that are important. So take out this spiral and turn it upside down, and you'll actually see that this is a left-handed spiral. So you go into the back of the board, you're coming out of the board, you're going into the board, you're coming out of the board, you're going into the board, back in the board, and so on. So it's a left-handed spiral and left-handed spiral. Also, solenoids. Don't try to memorize 50 rules trying to memorize concepts, okay? It's bad when you try to. So the whole point is, this is not a memorizing. So you memorize a couple of simple ideas and use them as building blocks. It's Lego. The world is made of Lego. So effectively, you have to learn how to take little things and learn how to build things. That's what you're expected to learn in university. You're not expected to be the brilliant person who memorizes a textbook, because those people, I'm sure there's somebody out there who can memorize a whole textbook and verbatim, but I don't think that the world is meant to be run by people who just memorize things. They're meant to be people who create new ideas, and hopefully that's what you're learning in physics. So imagine a solenoid. So again, so imagine you have a solenoid, and it's going into the board, I'll use dot, 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 dot. And coming out of the board, I'll use a solid. And going into the board, I'll use a dot, dot, dot. And going out of the board, and dot, dot, dot. And solid, dot, 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 dot. So here's a solenoid. Solid. dot, 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 going back into the board and coming out the board, and dot, dot, dot. And then I'm going to basically, so here's our solenoid, and I'm going to put the battery attached to here. So here's our wire. It's got a core, and we're wrapping wires, and this is a solenoid. And I'd like to know what the direction of the magnetic field is. So just to make sure you understand the idea, so this is going behind the board, coming back out, going into the board, coming back out, going into the board, coming back out, going into the board. So first question is this a right-hand spiral or a left-hand spiral? So did I put, oh, not enough dots here. Okay, so it's going out of the board. Okay, so we can ask ourselves, okay, take a line segment. Let's imagine we're taking this the first wire. Okay, before we do that, is this a right-hand spiral or a left-hand spiral? So imagine that I am turning this way. I'm turning this way and going this way, going in this direction. So if I do it this way, I should be traveling. If I'm going this way behind and coming back out, I would be traveling this way, but I'm not. I'm actually traveling this way. So this is a left-hand spiral. So whatever the spiral I did, I went forward, backward, forward, backward, forward, backward, forward, backward. So yeah, whatever. So going into so it's a left-hand spiral. Now the question is, what's the direction of the magnetic field? And there are many rules out there, right? And I don't want you to memorize all those rules. I just want you to remember one rule. And the one rule is, take out your right hand and get the orientation correct. So we know that the wire is going behind. I grab this wire, and the direction of the current, notice the positive side is this side, negative side is this side, so positive particles, which don't really exist, but doesn't matter. We know the electrons are actually the ones who are traveling, but we're assuming conventional current. Conventional current is always from the positive side of the battery into the negative battery. And so this wire is carrying current. And so if I grab this wire right here, grab it, and it's behind this solenoid core. So the center of this solenoid is called the core, right? And we're grabbing this wire, and we're grabbing it, and the direction of the magnetic field is going this way. So here's the wire. Here's the wire, it's going this way. Hopefully you can see this. It's coming out of the board and going into the board. And so in the core, right, if I grab this wire, it means that the magnetic field lines, right, would actually be going around this way. So this would be basically the North Pole, and this would be the South Pole. If just this one segment, it's curving, I know, but this cumulative behavior. Now if I take this wire and I go this way, and the center of the core, right here, the wire that's coming out of this board from here to here, I grab this wire. Remember, the current is traveling this way, going down. It's now coming out of the board. I grab it, and if I look at the center of the core, the magnetic field is going to be traveling this way. And in the core, right, in the center of that loop of the solenoid, the core, you'll actually see the magnetic field again is like this. So eventually you'll see that when you build up the answer, you'll actually see all these field lines are generating magnetic field lines like this, big loops like this, which I'm not very good at it. My drawings are horrible, but that's okay because I teach concepts. It's okay. So this is the North Pole and this is the South Pole, and you should actually prove to yourself at every segment of the wire. Try not to memorize 50 different rules, right? Like hand waves and pointing direction and stuff, or like derivative rules. I always consider these as derivative rules, like this way, or the finger current is I, magnetic field and the force and stuff, the fingers and stuff. Don't do that, because you defeat the purpose of understanding the minimal set of ideas. So minimal ideas and understanding of physics concept. So don't try to memorize 50 different rules just to pass an exam, because you're never going to remember it. The following day you can forget about it, but this one rule. So for example, if I'm in a car and I'm changing, here's our car. And here's the wheels, and here's the nuts of the wheel, and it's raining, and actually outside it's raining outside. Anyway, and I have to change and pull out the nuts, right? So nuts and threads are actually right-handed. So if I take out the wire, and the question is, how do I take this nut out? And so if it's a right-handed screw, it's a right-handed threads, and that's the the bolt. So what do I do to pull it out? So if I take my right hand and I turn this way, so here's my wheel, and take one of the nuts and I turn this way, it'll come out. If I turn the opposite direction, it'll go into the board, so it'll tighten the wheel. So for me to actually take this wheel off, I'll have to turn these 4 or 5 nuts, usually 5, right? In my car anyway, it's 5. Anyway, so we turn this way to pull out the nut, and I'm tightening, I turn in the opposite direction. Okay, so hopefully you understood what a right-hand rule is, and you remember one rule, one right-hand rule. Please try not to do this, because you defeat the purpose of actually, you're confusing physics, right? To have a set of simple ideas to build up concepts, and which basically you should be walking down the street and thinking of physics. It's not you just taking pen and paper, right, and just writing a bunch of equations. You're doing math, but the math is based on ideas, and those ideas you should be able to think about walking down the street or hanging onto a subway cart and thinking about these things. That's what I expect you as a physicist. Okay, anyway, hopefully you understood the idea of a right-hand rule.